When it comes to testing jet engines, one of the most critical components you'll encounter is the Bellmouth inlet. This specialized inlet is almost always installed on engines that are being evaluated in a controlled environment, such as a test cell. The Bellmouth inlet is designed with a very specific purpose in mind: to provide the engine with a smooth, unrestricted flow of air, closely simulating the conditions the engine would experience in actual flight, but within the safety and control of a ground-based facility. Its unique flared shape is not just for aesthetics, it's engineered to minimize turbulence and pressure losses as air enters the engine, ensuring that the data collected during testing is as accurate and reliable as possible. To achieve this, the Bellmouth inlet is typically outfitted with a variety of probes and sensors. These instruments are carefully positioned to measure key parameters, such as the temperature and pressure of the air entering the engine. Both total and static pressure readings are taken, which are essential for engineers to understand exactly how the engine is performing under test conditions. The data from these probes allows for precise calculations of engine efficiency, airflow rates, and overall performance. Technicians meticulously install and calibrate these instruments before each test, ensuring that every reading is accurate and that the engine's behavior can be thoroughly analyzed. During the testing process, it's absolutely vital that the air entering the engine is as close to ambient, outside static air as possible. The Bellmouth inlet is specifically designed to allow this air to flow into the engine with minimal resistance or disturbance. This is crucial because any restriction or turbulence at the inlet could skew the test results, making it difficult to accurately assess the engine's true capabilities. By providing a smooth, laminar flow of air, the Bellmouth ensures that the engine is tested under conditions that closely mimic real-world operation, without the unpredictable variables that might be present in an actual flight scenario. Another important aspect of the Bellmouth inlet is its integration with the engine test stand. The Bellmouth is securely attached to the movable part of the test stand, which means it moves in unison with the engine during testing. This setup is essential for maintaining a consistent and sealed airflow path, regardless of any adjustments or repositioning that may occur during the test. By moving together, the Bellmouth and engine ensure that the airflow remains uninterrupted and that the measurements taken are not affected by any misalignment or gaps that could otherwise introduce errors into the data. The test stand itself is a sophisticated piece of equipment, typically composed of two main components: a stationary non-moving base and a movable section to which the engine and the Bellmouth inlet are attached. The stationary part provides a solid foundation, anchoring the entire setup securely within the test cell. The moving part, on the other hand, allows for precise positioning and adjustment of the engine during testing. This two-component structure is crucial for accurately measuring thrust and other performance metrics, as it isolates the forces generated by the engine from any external influences. Together, the Bellmouth inlet and the test stand create a controlled environment where engineers can gather the detailed, high-quality data needed to evaluate and refine jet engine designs, ensuring they meet the rigorous standards required for safe and efficient operation. In the world of jet engine testing, precision and accuracy are absolutely critical. The entire setup you see here is meticulously engineered to ensure that every aspect of the engine's performance can be measured and analyzed in detail. One of the most important components in this process is the thrust stand, which is designed to allow the moving parts of the engine to push directly against a highly sensitive load cell. This load cell acts as the heart of the measurement system, converting the physical force generated by the engine into precise digital data that engineers can use to evaluate performance. As the engine runs, technicians closely monitor the thrust measurement equipment, watching the digital displays for real-time readings. These measurements are crucial, as they provide immediate feedback on how much thrust the engine is producing under various conditions. By analyzing this data, engineers can make informed decisions about adjustments and improvements, ensuring that the engine operates at peak efficiency and reliability. The accuracy of these measurements is vital for both safety and performance, especially when developing new engine designs or testing modifications. A key feature of this testing environment is the Bellmouth inlet, which is specifically engineered for aerodynamic efficiency. Unlike the inlets found on operational aircraft, the Bellmouth is designed with a single, focused objective: to allow air to flow into the engine as smoothly and efficiently as possible. Its shape is the result of extensive research and engineering, aimed at minimizing any disturbances or resistance to the incoming air. This ensures that the engine receives a consistent, undisturbed airflow, which is essential for obtaining accurate test results. The Bellmouth itself is essentially a bell-shaped funnel, carefully crafted with rounded shoulders and a smooth, continuous surface. These design features are not just for aesthetics. They play a critical role in reducing turbulence and preventing the formation of vortices that could disrupt the airflow. By offering practically no air resistance, the Bellmouth allows the engine to operate in ideal conditions, free from the complications that can arise from less efficient inlet designs. This attention to detail is what sets the Bellmouth apart as a vital tool in engine testing. When we talk about duct loss, we're referring to the amount of energy lost as air moves through the inlet duct. In the case of the Bellmouth, this loss is so minimal that it's considered virtually zero. This is a significant advantage, as it means that the engine's performance can be measured without the need to account for the inefficiencies that are often present in standard aircraft inlet ducts. Visualizations of airflow around the Bellmouth clearly show how smoothly the air enters the engine, with almost no disruption or loss of pressure. Thanks to this highly efficient design, the engine can be operated in the test cell without the complications and performance losses that are common when using typical aircraft inlet ducts. This allows engineers to focus on the engine itself, knowing that the data they collect reflects the true capabilities of the engine, unclouded by external variables. In summary, the Bellmouth inlet is a critical component in jet engine testing, enabling precise, reliable measurements and supporting the ongoing pursuit of greater aerodynamic efficiency in aviation technology. Measuring engine performance is a critical step in understanding how well a jet engine operates under controlled conditions. In specialized test cells, engineers gather a wide range of data to evaluate the engine's capabilities and efficiency. One of the most important parameters measured is the rated thrust, which tells us how much force the engine can produce at maximum power. This value is essential for determining whether the engine meets its design specifications and is suitable for use in aircraft. Another key measurement is thrust-specific fuel consumption, or TSFC. This figure indicates how efficiently the engine converts fuel into thrust and is a crucial factor in both performance and operating costs. To ensure the most accurate readings, a Bellmouth inlet is often used during testing. The Bellmouth inlet provides a smooth, controlled flow of air into the engine, minimizing turbulence and allowing for precise measurement of airflow and engine output. For safety and to prevent foreign objects from entering the engine during these tests, the inlets are usually fitted with protective screening. This mesh acts as a barrier, ensuring that debris or loose items in the test cell environment do not get sucked into the engine, which could cause damage or affect the test results. However, the presence of this protective screen does have an impact on the test data. As air passes through the mesh, a small amount of efficiency is lost due to the resistance created by the screen. When extremely accurate engine data is required, such as for certification or research purposes, engineers must carefully account for this loss. They use correction factors or additional measurements to ensure that the reported engine performance truly reflects the engine's capabilities, compensating for any disturbances caused by the protective screening.